first we say that T3 is in the first permutation. And then we check this condition. So if the distance between U, any vertex, and that T3, if this distance is less than alpha times distance between AU, it means AU is the minimum distance between, the closest terminal, the distance between the closest terminal to U and U. Here, because that terminal is also T3, so and alpha should be, for example, we pick alpha is 1.5. And because the distance between U and T3 is smaller than 1.5 this distance, so T3 we can assign U to U and V, both of U and V, so it's like a mother that T3 protects them. U and V are assigned to terminal 3. So we have protected them. So T4 cannot. So T4, when he wants to cut, and then he cannot pick U and V anymore because it is picked by the previous permutation. So if he chooses another radius, so he picks like this. But if something is here, it is already assigned to T3. So T4 cannot assign vertices that are already assigned. So he has to pick another vertex that is not assigned. And that's why in this algorithm we put unassigned here. And using this, we can prove that all of the vertices should be assigned by the end of the algorithm. So T3 is like parents, mother and father, that protects U and V from further permutations, further terminals that should pick one of them and say, hey, U and V, you should assign yourself to us, not to someone else. But T3 is like, because it is the closest terminal to U and V, it protects them from the next rounds. So you see why this HK, which is 1 plus 1 over 2 plus, this plays an essential role. So it all depends on who is first. So this permutation here is very important. So because if you find the probability of the cut that edge U and V is cut, then if you reduce this probability, then it implies that you have reduced the LP value. So if you reduce the probability of U and V being cut by some terminals, if you reduce that, then you can reduce that D of U and V. Of course, it has some cost as well, U and V. So if you reduce this, it means that whenever there is a cut, one of them is 1, the other one is 0. It is rounded to that, and if you reduce this probability, then you have reduced the LP value, and that is your goal in order to find a better approximation, a lower factor for approximation, and that's it. So it's a very natural and interesting algorithm. So So first, I want to prove something, and then after that we go to correlation clustering, which is a fundamental and good primitive for future generation of algorithms in cut-related problems. For example, multi-way cut, K-cut, ST-cut, and many different cut-related problems. Minimum congestion, all of them. So there is a lemma in that article, the Kalinsky article, that says that we fix U and V in V, and delta to be between 1 and 1/4 minimum of AU and AV. So the probability, because as I said, the important thing is to reduce the probability that U and V are separated. So this lemma says that the probability that U and V are separated is less than equal to 4 HK, that's harmonic number, people say, times delta AU plus delta AV. So if we just reduce this probability, then automatically we have reduced the LP value. Because the LP value should be less than that expectation, and expectation comes from the probability, and if we just, it suffices to bound this probability in order to have a good and small approximation factor. So h of k, as I said by definition, is just 1 plus 1 over 2 plus 1 over k. So you see, this probability that U and V are separated has an inverse relationship to the distance between U and the closest terminal. Also, it is inversely related to distance V and terminal. For example, if U and V are here, and AU, AU is the smallest terminal that is close to U, and AV is the smallest terminal that is closest to V. So if AU and AV are big, if AU is big, AV is big, so the overall number becomes small. So if they are very far apart, so if AU and AV are very far apart from U and V, then the probability that U and V is being cut is very, very small. What this suggests, it suggests that U and V is here. It is better to AU and AV to be too far away from this U and V. What that means, it means that it leaves some rooms for other terminals to be here. For example, terminal 1, terminal 2, terminal 3, terminal 4, terminal 5. And because these terminals, if they are in between them, then they have the chance to be assigned to U and V much sooner than AU and AV. So that's and the probability of being cut is less, because if you remember, if delta U and sigma j, for example, here is sigma j, T1 is sigma j, is for example, sigma j is here. If delta of U and sigma j is less than alpha AU, now AU is too far. You see, AU is too far. Then we assign U to sigma j. So you see how we can bound this probability that U and V are separated. So the probability that U and V are separated, being cut. I mean, Itai Abraham says U and V are cut. What is the probability? So we have used this in, if you remember, in metric embedding, we have used this in that framework. In that framework, we used the article of Itai Abraham. And now we want to show that why this is the case. And there is a lemma that says that expectation of the distance between F and U and F and V is less than 38 HK delta of U and V. So this is delta, and this is, they call it S of U and V. So we go case by case, and by saying that, for example, S of U and V can be written as the distance between F of U and F of V, and we just use the triangle inequality. So this is the delta F of U and U plus delta U and V plus delta V and F of V. And because this is less than 2AV, this is less than 2AU, and so S of U and V becomes less than 2AU plus delta U and V plus 2AV. You can use all of these cases to prove that this holds. So it's a very simple proof. But the theorem, if you look at the article, the theorem 2.4, it says that there exists a randomized polynomial time O log k approximation. So this is just the original CKR algorithm, not the modified and better algorithm by Talvar, which was O log k divided by log k. So it is an older result. That's why it's worse. So there is an randomized polynomial time approximation for zero extension. So in 2003, they tried to improve that. I mean, people like Talwar and Satish Rao. Satish Rao also wrote an article about recently about metric embedding. Kunal Talwar, an improved approximation algorithm for zero extension problem. This is the title. And they get, as I said several times, log k over log k, which is quite an improvement. And so the older they improved and outperforms the older results of Kalinsky and Karlov Rabbani, who used log k approximation for general graphs. So the beautiful special case is when the d of t and t prime is 1. So we want to minimize c of u and v. So it's like a multi-way cut, as I said several times. So zero extension, as I said, is a natural generalization of multi-way cut and is also a special case of metric labeling problem of Kleinberg and Tardus, as I said. So metric labeling, in metric labeling, people like Kleinberg and Tardus proved that you get log k, log k. People like Kleinberg and Tardus. So let's forget this, and so any solution to zero extension problem, J is equal to C of U and V, D of F of U and F of V. Because this is log K delta U and V using CKR algorithm, And so instead of solving C of U, V, delta of U and V, so this is it induces a semi-metric such that U and V is D of F of U and F of V. And so J prime is greater than J. So this problem is a lower bound for J. And you get this approximation if you use CKR algorithm. But you can improve that using the Talwar algorithm, which is a better CKR. Of course, there is an improved integrality gap for CKR by Makarichev in 2016. Also, it is an interesting article, Buchbinder and Naur 2013, exponential clocks. But let's come back to our problem and see it from a different point of view. So we have this is V, this is U. As I said, the closest terminal to U is AU. Also, our bad terminology, also this distance is called AU. So the minimum distance is AV, and the terminal associated to that minimum distance is AV. And we have another terminal as well, T. So this distance, A, and distance is T of T and V. So if you just observe what we are doing is that for V,